about the raw numbers required when it comes down to what you need in order to build immersive virtual reality. And that's what this talk is kind of all about. Just kind of thinking about it from a data standpoint. What is virtual reality? Whoops. Oh, no. Okay, well, I had a video here. Movie came out recently, Ready Player One. It's okay. But it's all about virtual reality. The main character, whenever he wants to escape from his world, he puts on a pair of glasses and logs into the Oasis, a video game that allows him to move his head around and look around the world, walk on a treadmill, and even move his body and interact with things. His body, to him, his body is living inside this video game. And it seems like a pretty awesome place. The whole movie is all about him saving the paradise that is the virtual world. This is the virtual reality system I built for the rats. It's not quite a paradise. We're getting there. In this one, we track the movement of the rat or mice, and use that to reconstruct the virtual environment that the rat's supposed to see. In this case, the world is projected onto the walls and floor of the arena. This rat is looking on one side or the other of a board that he's sitting on and trying to decide which side he wants to jump off of. The side he's looking on now, it looks to him like there's a cliff. And rats are really kind of anxious creatures. They don't like to jump off of ledges. If you're doing an experiment with a rat and you put him onto the table and you go for lunch, he'll still be there when you come back. And our rats, when they see these virtual cliffs, they decide they don't want to go there. They go away from it. And that tells us a lot about whether or not they perceive virtual worlds. VR has been around since the 60s, but only now is it really hitting the consumer space. And it has to do with this company, and with the things that they're selling, these graphics cards. Now they're labeling certain models of their graphics cards as VR ready. And what VR ready means is that they're really expensive. They're expensive because they need to be fast. The faster ones are more expensive. And it's kind of strange that we've had VR since the 60s, but you need a powerful graphics card in order to have VR. What is the relationship between powerful graphics card and VR? That's what all this is talking about. Why do you need to pay so much to get a VR system in your home? Well, the first problem that you face when you want to build a VR system is you need to be immersive. That means you need to be able to fill the viewer's entire visual field. Actually, right now, most are only 130 degrees of the visual field. Although we can see 210, so we're still getting there. With space. If you don't have that, you have it more like this, you get comments like this for the 1996 Sony Glastron, creator of Doom. Not immersive whatsoever. Now, a model called the PMax is coming out, and it can see 200 degrees. So we're finally getting to the point where we can start to become really immersed by a VR system. But a bigger screen means, well, it means a bigger screen. It also means you need more pixels. You could just make the pixels really big, but then you get an effect called the screen door effect. Seen in the middle, it really looks like you're looking through the screen door. You have the sensation that there's something in front of your face, which isn't very nice. And if you look on the right side of the screen, if you have really big pixels, everything looks blocky. And that's not just a problem for how the fidelity of the image is. It's also a problem with motion tracking. Whenever you rotate, the world should move the opposite direction, right? You move left, the world should move right. But if you have one pixel in big steps, you're discretizing your world. That means you need to move the size of a pixel in order for it to be able to adjust. And that's a real problem. So you need to have small pixels over your entire large screen in order to do this. And can you see where I'm getting at now? It's going to mean you're going to need a lot of pixels. How many pixels are you going to need? Well, you're going to need as many as your visual system can deal with. I mean, that's the maximum threshold. We have a sort of pixel-like system in our eyes. Pixel-ish. Rod and cone cells in the back of our retina. Each rod and cone cell is a vision. It's the light receptor that's in our eyes. We have a bunch of them. We have one cone every hundredth, thousandth of a degree, no, 8 thousandths of a degree in our fovea. That's the center part of our eye. That's where the concentration of the image really is. And when you start thinking about how many pixels you would need to hit every cone, well, you need about 432 megapixels in order to cover that entire visual space.
I had heard before that 8 megapixels was more or less where we could not identify. I don't know where this is coming from. Maybe at a larger distance, maybe.
It's coming from Apple. Yeah, the retina display. The pixels are so small you can't see them as long as you hold the screen away from your face. That's the problem. They're talking about the distance. Well, most people are talking about pixel size. They're talking about distance from eyes, and they're talking about it for certain conditions, like reading text or viewing an image. And you can and different pixelation of an image affects you for different types of tasks. When it comes to motion perception, it's a lot bigger problem.
Because there's also this discussion about if are we in a virtual world or in a simulation, if we are someday getting our VR so good that we cannot differentiate from the real world. Mm-hmm. There's the higher possibility that we are already there. If
that's true, if that's true, and I don't have to answer your question, you're just a virtual participant, doesn't matter. No, yeah, it could be. It could be the case. There's a thing called a simulation theory, and a lot of it comes down to information content. If you have if you simulate the universe, and you can simulate every bit of it, then you might as well have a universe in your simulation. So why not?
So this is the real number.
Well, it's a real-ish number. This is a good approximation to start with. Now, one thing that we forget about when we talk about different resolutions is that it's not a linear effect. When you go from a 720p screen to a 1080 screen, we're talking about the vertical resolution. You also have to get more pixels in that square. So you need to cover the whole area. So when you go from 1080p screen, an HD screen, to an HHD screen, a really high definition screen, you have to be able to draw all of these pixels at the same time. Now there are 8K screens going out. These are super processors. And you need to deal with all that data. If you're not used to working with graphics, just think of them as arrays and how intimidating it would be to deal with arrays at that size. One solution that people are coming up with is called foveated rendering. Foveated rendering is when you render different parts of your image at different resolutions depending on where it is relative to the eye. Some people use eye tracking for this, but if you have well, you can't actually have to use eye tracking for this, but if you know where the eye is looking, what you could do is render the center of the image in high resolution and the rest in just blocky, blurry resolution. And that would work quite well. Now people are even designing screens that work that way. They're attached to motors that actually move the screen at high speeds in order to try to keep pace with the eye. If you can do this well, and it's really, really hard to do, then you don't even have to put pixels on the edges of your screen. You can have a lower resolution screen, which means you don't have to deal with as much data. Right now it's just a rendering process. And this is kind of the idea of the fovea. Most of your color vision is at the center. Most of your motion vision, these rods are at the edges. And since our details are from the cones, then this works quite well. Oh, sorry. Yes.
What about the movement problem if you have bigger pixels on the sides? Then can't you still tell that the movement is in pixel quantized ways?
You would be able to if you had that resolution. Unfortunately, even at the widest, the cones the rods don't have the same resolution as the rods, and they also don't have as high light sensitivity, and that helps a lot when it comes to this problem. And it's an effect that I'll bring up in a moment. One solution that has become popular in the VR space is to use flat shade environments. Does anyone notice this? That the popular games all look cartoony? Well, the whole motion problem is part of it. You see, your eye only detects changes, and when you move your head, the only things that your eye is actually picking up are where these edges change. And if you don't have many edges, then then the latency or that you have to deal with, or the timing that you have to deal with is less. The brain is getting flooded with color information and only gets a little bit of motion information, and the effect in the end is a much more immersive environment. So even though we want a VR system that looks like this, the solution at the moment is to make worlds like this, and you feel more immersed in this kind of environment. You also have to you can't just display the world, you have to display it quickly. So what do I mean by quickly? Well, first of all, you've got refresh rate. In order to see motion on anything, right now we're doing it by images, one at a time, right? Shown in sequence. Not all displays in the future are going to work that way. There's some really cool changes happening in that space. But right now, you're showing a single static image, one every whatever hertz, ever milliseconds. Okay. At 30 frames per second, you start seeing something that starts to look like an image. Right now, this looks a little bit kind of blocky still, even at the fastest speed, right? It's a little too slow. Of course, most movies are shown at 24 frames per second, even slower than this, and we accept that just fine. But when it comes to video games, you start getting demands at about 60 frames per second before people stop complaining. But you can perceive rates over 480 frames per second. I can't show that on the screen because the screen only shows up to 60 frames per second. But if you come to my laboratory, I'll show you much faster motion. Whenever you get into discussion in the future, and if you remember nothing else, just remember this: the limit of human speed perception is not 50 hertz. I hear that all the time. They say you don't need anything faster than 60 hertz because the eye can't see faster than 50 hertz. And that's not true. Where does that come from? From our flicker fusion frequency, the FFF. Our cones only have a limited speed at which they can which they can fire relative to when a new photon hits them. Okay, and if they need a little bit of time between each packet, basically. The stronger the light change, the faster they can fire. But this starts to hit a limit at about 50 hertz. But so if you are having an image that's blinking on and off really fast, once you get above 50 hertz, you can't notice that any blinking is happening at all, and that's really nice. Most of our LEDs work this way. We use pulse width modulation in order to trick the brain into thinking that a light is on constantly when in fact it's blinking. But when it comes to motion, you're starting to interact between cones, and the brain is really sensitive to that. Imagine a machine learning problem where you have not one or two variables, just light intensity. You have 1,000 variables to work with. You can fit all kinds of models like that, and our brain has done that through evolution and our own development. In addition, you have another kind of speed. You have display lag. Now, this isn't talked about very much in the display world, but it's starting to. You're starting to get video projectors and monitors that are called gaming monitors. Gaming monitors means it takes less, it's like a marketing term. What they mean is that it takes less time between when your graphics card says draw this image and when the screen actually draws the image. Right now, a lot of monitors, they can take 2 or even 3 frames before they decide to actually show you what they were supposed to show you. That may mean you have 50 milliseconds of latency before you even have to worry about draw speed. Gaming monitors usually have only 1 frame of latency. So just because you said draw something now doesn't mean it will draw it exactly now. And when you get that, you get VR sickness. Latency is a real problem with related VR sickness. Any longer than 20 milliseconds of latency, and people start to feel sick. Not all people. Some people are really sensitive to it. Some people just aren't. They used to think that 20 milliseconds, or that 16 milliseconds was our limit of our brain's limit to how it can tell the difference between when we moved and when our world moved visually. Turns out that's not the case. Both of the original studies that show this were using screens that were 60 hertz. And 16 milliseconds is, 60 hertz is 16 milliseconds. It was the fastest they could display. They never tested faster. And so we're doing that in the lab right now and finding people are really sensitive. In fact, neuroscientists that are studying mammals have to worry about other kinds of systems. Turns out flies have motion sensitivities that require screens of over 100 hertz. This is a specially designed display used only for fly virtual reality. Each one of those is made up of LEDs. It doesn't have to have as high resolution because flies don't have as high resolution, but it does display at 300 frames per second. How did they know all this? Well, they showed flies moving stimuli and then put electrodes into their eyes and just recorded the frequency spectrum of the response. And they always got this 100 hertz peak until finally they got above 100 hertz and it disappeared. So if you want to use your pet fly for your virtual reality system, it's not going to work. You're going to need to buy a better display. All in video. It'll work out. Of course, displaying is not the only problem, and that's not the only data you have to worry about. You have to record the motion of the person as well. We've got there are two kinds of systems that are being used. One is usually a camera system, and HTC Vive uses a completely different system called the Lighthouse system. And the other one is our accelerometers, the kind you find in your phone that can tell whether where your phone is moving, whether it's in portrait mode or landscape mode. They have different update rates too. The video systems can be anywhere from 30 to 360 hertz. Most are about 60 hertz, although some are like webcams and they're just 30 frames per second, which is terrible. So that means you already have 16 frames per second of latency just from the display lag. And then, but accelerometers are really fast. The only problem is that accelerometers, where is, there it is. Accelerometers get error. All they do is to detect motion, which means that as you can go from motion to position by just saying the difference from now to later, but if you add up those motions over time, you start to kind of drift off of the actual position. Most systems now combine the two together in order to get a more accurate response. And all these delays, they add up. First, you've got your tracking delay. Then you have to actually send the data to the computer. You have to actually render the image. You have to send it to the display and then actually show it to the person. And you need to keep that as low as possible. And it's not just about the delay of the single image. You also have to remember that your display isn't drawing all those pixels at the same time. It's drawing every line one at a time. Well, actually, every pixel at a time, but the lines matter the most. If you imagine this as a rectangle and someone moving over time, then the top part of the rectangle will be drawn before the last part of the rectangle, which means the rectangle, as you're moving, would look tilted. To deal with this, head-mounted systems turn all of their screens to the side. They draw it vertically because we move our head left to right more often than we move our head up to down, and that's how they solved that problem. So that worked out pretty well. Camera data is really, really hard to process. You have a lot of it, and you often have a lot of cameras to know where the person is in space. I think some systems only require 2. In my lab, we have 8, and soon we'll have 16, which means we have 16 high-resolution cameras and all of their data coming in at 360 frames per second that need to be processed by the computer. The solution these days has become to put computers on the cameras themselves to start trying to cut down that data before it's sent to the central computer. So a lot of cameras are now including FPGAs and special frame grabbers in order to process that data as soon as it arrives for anything. Of course, we know that if we want a 3D world, we need to show a different image to each eye, right? You need to show one to the left eye and one to the right. That's why we wear special 3D glasses at the keynote. But this has a problem for latency too. Depending on which kind of system you're using and how you do everything, you could have anywhere from 0 latency for stereopsis to an extra 16 milliseconds of latency if you're rendering at 60 hertz. Researchers are spending a lot of time on this now. This is a praying mantis. You see how he has a green goggle and a blue goggle? They're glued to his face. He can't take them off, unfortunately. But they've got a special VR system just for this guy to understand what the limits are for the praying mantis in order to understand the 3D location of something. if we, each of these technologies has a different impact on resolution. If you're looking at an active shutter glass situation, for example, these powered glasses, what these glasses are doing is they're turning on and off alternatively. Your screen is a 2D screen, and every other frame, it's sending a data to the left or the right eye, which means that your one eye is always getting data after the other eye. That's not a good thing for virtual reality. If you got two screens, you might slow things down just by having to render two screens. Usually what they do is they cut the screen in half, and they just send the data all to the same screen at the same time, but of course this cuts your resolution in half, and it's just a nightmare. If you have polarized glasses, you might not be out of the field yet. If you have a single monitor and you bought a really cool 3D monitor there, and they give you polarized glasses, what's happening in that one is they have the same kind of system, but in the projector, and what it's doing is not flipping on and off, it's flipping between vertical and horizontal polarized light. And that means, well, left eye, then right eye. That's another 16 frames per second, and now your eyes are receiving information at different times. Unless, of course, you go to a really nice keynote. They might show information at the same time. How do they do that? Well, they have two projectors. One projector for the left eye, one projector for the right eye, no problem. Turns out the best and cheapest and fastest way to do things is the old-fashioned way, red and blue. Or if you can't see red like this guy, blue and green. Color data gets delivered to the screen basically at the same time. So if you're okay with playing monochrome VR games, maybe you should be putting on these glasses instead. There's so many complex solutions that are being conceived of in order to get around the latency problem. In VR, latency is everything. And this may mean that the tracking data you send in to the initial rendering pipeline ends up getting fed in multiple times in order to correct for those errors. There's all kinds of complex models that are coming up with. And if you enjoy building complex data models, VR really might be an interesting field for you. Now, I'm not saying that VR is in the future. We can't have VR now. Obviously, we have VR now. It's awesome. And you can be immersed by it. It's just, we're not quite there yet. Next time you put on the VR glasses, pay attention to what you can see outside your field of view. Try to move your head faster than this. Once you start doing those kinds of things, latency will start to become a problem. And in the future, you won't have to think about it. You'll just be there, and maybe you won't be sure if you're in the VR world or you'll be outside it. Thank you.